Okay, so let's look at a few important theorems or results relating to eigenvalues and eigenvectors. Some important facts, let me call them. The first one is that if you take a Hermitian operator, and we had defined Hermitian operators last time. For a Hermitian operator, uh, let's call it omega, the eigenvalues are always real. Now, in the examples that we did, they were always real numbers. I didn't show you any complex valued ones. But see, in general, you're getting some polynomial. No? You're getting the characteristic polynomial lambda, in lambda, and the solutions to those can be complex also. But if your matrix is a Hermitian matrix, then you're guaranteed that the eigenvalues are going to be real numbers. So how do we prove that? Uh, so the eigenvalue equation for this omega is as follows. So omega v is lambda v, where lambda is the eigenvalue. If you took the complex conjugate, or rather the complex conjugate and transpose of this equation, then you would get complex conjugate and transpose. You would get omega adjoint acting on the bra v, giving you bra v and complex conjugate lambda. We saw last time, no, how to do complex conjugate transpose or adjoint of an entire expression involving vectors, scalars, and operators. Okay, so now let us take the inner product of the first equation with this bra v. So I'll get and for this bottom equation, I'm going to take the inner product with ket v. Now if you compare these two equations that we have over here, and given that we are looking at a Hermitian operator, so omega is the same as omega adjoint. That's the definition of a Hermitian operator. So from these two, since the left hand sides are equal, the right hand side should also be equal. Therefore, lambda should be equal to lambda star. Means the eigenvalue and its complex conjugate are the same number. Therefore, lambda has to be a real number. Okay. The next result that I want to talk about is that if you take, and again, I'm again talking about a Hermitian matrix. And the reason I'm talking about a Hermitian matrix is that in quantum mechanics, we are usually going to be talking about Hermitian matrices. So the eigenvectors of a Hermitian matrix are all orthogonal to each other. So they're mutually orthogonal. And so we can use them as a basis. So they form a basis of the vector space. I'm not going to prove this result, but if you want to see the proof, you can find it in any good linear algebra book. Possibly Shankar also discusses the proof, but I'm not sure. But in general, if you pick up any mathematics book on linear algebra, you'll be able to find the proof over there. The third one, and this is kind of important, and this is in some sense the physical meaning, or rather the geometrical meaning of eigenvalues and eigenvectors. So I said that eigenvectors were those directions that only get stretched under the operation, and eigenvalues represent the amount of stretching that they experience. Now let's say I give you a matrix, and for simplicity let me take a 3 cross 3 matrix. If I give you a matrix A which is 3 cross 3, and you find its eigenvalues and eigenvectors. So let's say its eigenvalues, you found them to be lambda 1, lambda 2, lambda 3, and you found the corresponding eigenvectors to be some column vector with 3 entries. So v1, v2 and v3. What you can do is you can take these 3 eigenvectors together and okay, not so I said eigenvector means it can have any length, but you take the normalized eigenvectors. So you take the vector v1 and you normalize it, take the vector v2, normalize it, take the vector v3, normalize it. Those normalized eigenvectors, if you stack them up next to each other, so v1, v2, v3, you agree you'll get a 3 cross 3 matrix. This 3 cross 3 matrix is unitary. Not just that, if you calculate what is U adjoint A U, what you will get is a diagonal matrix, and the diagonal entries will just be the 3 eigenvalues, lambda 1, lambda 2, lambda 3, and zeros everywhere. Now in the last video lecture towards the end, I had said that this is called a similarity transformation. And it represents a change of basis. So when we are when we are finding eigenvalues and eigenvectors, and this is the crucial part, so listen to this carefully. When we are finding the eigenvalues and the eigenvectors, what we are doing is we are basically constructing a unitary change of basis with the vectors v1, v2, v3. We are choosing to go to a different basis, and by implementing this similarity transformation, we are going to that basis in which the matrix A becomes diagonal. So this is nothing but the matrix A, but in a new basis where A is diagonal. That is why the process of finding the eigenvalues and eigenvectors, the whole eigenvalue problem, is also sometimes referred to as the process of diagonalization. Let me explain this to you in a slightly different way. Suppose I give you a matrix A. This matrix A, in general, it's not a diagonal matrix, right? It has elements all over the place. But you know that the elements of a matrix depend on what basis you are writing that matrix in. If you change your basis, the matrix will look different. As we have seen before, if you want to find the elements of a matrix, let's say I give you a matrix A, then the elements of this matrix A, the ijth element is given by this A sandwiched between bra I and ket j. I and j being the being the basis vectors. So clearly, what that matrix element is depends on what basis you have chosen. If I ask you to go to a basis in which the matrix A is diagonal, what you need to do is you need to find the eigenvalues and the eigenvectors of the matrix. You take the eigenvectors, stack them together and make a unitary transformation, a unitary matrix. And then if you do this U dagger AU, you will have changed the basis, and in the new basis A will be diagonal and the diagonal elements will just be the eigenvalues. One crucial point, in general, there is, if I give you any random matrix, there is no guarantee that it can be diagonalized. But that guarantee exists if your matrix is a Hermitian matrix. So every Hermitian matrix can be diagonalized using a similarity transformation. And this diagonal matrix, which has those eigenvalues, is just called, sometimes it's called A diag, just to indicate that it's that matrix A but in a different basis, a basis where it is diagonal. Just to remind you one more time, how do you check if a matrix is Hermitian? You have to take its complex conjugate transpose, which is called the adjoint. So complex conjugate and transpose, and this should be the original matrix itself. This is the definition of Hermitian. How do you check if a matrix is unitary? You have to check that U adjoint is the same as U inverse. Or a more useful way of doing it is you can check row unitarity or column unitarity. Do you remember this? This is something we saw in the last lecture. Basically, you take the rows or the columns of your unitary matrix and check that they act like orthonormal vectors. Then if that is satisfied, then you know that your matrix is unitary. The next property I want to talk about is what happens to the determinant of a matrix when you diagonalize it. So you know that determinant, okay, wait, if I take A diagonal, this is U dagger A U. So let's take determinant of both sides. But determinant of a product of matrices is just the product of their determinants. And because U is unitary, therefore U adjoint is U inverse. So I can write determinant of U inverse But determinant of U inverse is just 1 over determinant of U. So these cancel. So therefore I get that determinant of A diagonal is just determinant of A. So when you do a similarity transformation, the determinant doesn't change. Even after change of basis or after a similarity transformation. Not just that, one more interesting thing. What is the determinant of a diagonal matrix? So this is determinant of just lambda 1, lambda 2, lambda 3. And you can just calculate it, it's trivial. It's just the product of these eigenvalues. Lambda 1, lambda 2, lambda 3. So in general, this is the second important point over here on this page, that the determinant of any matrix A is just the product of its eigenvalues. I can do something similar, and that is the next point. And now we are going to be talking about trace of a matrix. I hope you have seen traces of matrices before. Trace of a matrix just means you are adding up all the diagonal elements. So again, if I take U dagger A U is equal to A diagonal. Now if I take trace on both sides, now trace has an interesting property, which is that if you have a trace of, let's say, some 4 matrices, you can cycle them around in cyclic order and the trace will remain the same. So you can write B, C, D, A. See, I'm always cycling them around. I'm changing them in a cyclic order. C, D, A, B. Trace of D, A, B, C. This is a property of trace. So over here, I can bring the U on this side. I'll get U dagger A is trace of A diagonal. But U dagger is just identity. That's the definition of a unitary matrix. Therefore, trace of A is trace of A diagonal. So on this page, we are seeing that trace doesn't change or remains invariant. Under a change of basis or similarity transformation. Not just that, what is trace of a diagonal matrix? So the diagonal matrix is lambda 1, lambda 2, lambda 3 and zeros everywhere. So if you add up, this is just lambda 1 plus lambda 2 plus lambda 3. So which is the sum over all the eigenvalues. So for any matrix A, the trace is just the sum of all the eigenvalues. All right. The last main topic that I want to discuss is how to write functions of operators. So suppose given some operator omega, how do I calculate e to the power omega or sine omega, other such functions? Algebraic functions are okay. Omega square, omega cube, that you know how to do. You just multiply the matrix with itself. But how do you do e to the power omega? So for that, we look at the Taylor series expansion. So for real numbers, we know that e to the power x, so I'm taking e to this exponential function as an example, but you can do the same thing for sine, cosine, any other function that you might have. E to the power x, we know the Taylor expansion is 1 plus x square by 2 factorial plus x cubed by 3 factorial and so on. This is the Taylor series expansion of this. So do the same thing for the operator as well. So 1 plus omega square by 2 factorial. Now this is not the easiest thing to calculate. So what we can do is the following. Let's multiply on both sides of the equation by u dagger and u. So I'm saying u dagger e to the power omega u is u dagger, well, I'll do it term by term. By the way, I should call this identity. So u dagger identity u plus u dagger omega u plus u dagger omega square u and so on. Now see, this still gives you identity. This gives you u dagger. What is u dagger omega u? This is omega diagonal. The matrix U that I'm using is that U is basically the eigenvectors of omega stacked together. So this is U omega diagonal. Over here, what I'm going to do is omega square is omega times omega. Let's write this in a different color. U dagger omega square u from this term is u dagger omega u. Between those two omegas, I'm going to sandwich a u dagger because u dagger is just identity. So I can put this anywhere. Now see, u dagger omega u. This becomes omega diagonal. Again, u dagger omega u becomes omega diagonal. And same thing I can do for the omega cube term, the omega 4, omega 5. Everywhere between every two omegas, I'll sandwich u dagger and I'll end up with omega diagonal. So this becomes omega diagonal square by 2 factorial and so on. So what I have now over here is basically e to the power omega diagonal. Now this is easy to calculate. Why do I say that? Because this is just 1 plus lambda 1, lambda 2, lambda 3 and so on. This is 1 over 2 factorial, lambda 1 square, lambda 2 square, lambda 3 square and so on. 1 over 3 factorial, lambda 1 cube, lambda 2 cube, lambda 3 cube and so on. That means element by element you are going to get, what was the left hand side? U dagger e to the omega u. Element by element I am getting e to the lambda 1, e to the lambda 2, e to the lambda 3 and so on. Therefore, now if I left multiply by u and right multiply by u dagger, I'll get left multiply by u right multiply by u dagger. So this is identity, this is also identity, so I just get e to the omega is u, e to the lambda 1, e to the lambda 2, e to the lambda 3 and so on. So if you don't know how to calculate e to the power omega for any random matrix omega, you just calculate e to the power of its various eigenvalues and then left multiply by u, right multiply by u dagger, and that's how you get e to the power omega. Basically, it's much easier than having to find all of these infinite omega square, omega cube, omega 4 and so on. You just take e to the power of these eigenvalues and put u and u dagger on both sides. This was for exponential. In general, the same mechanism you can use also for sine, cosine, etc. Applications of this whole eigenvalue, eigenvector business, of course, in quantum mechanics we will use them extensively. But like just to give you a more physical feel, you can also see it in classical mechanics. So in classical mechanics, what happens is in your 12th standard, you were told that the angular momentum vector is, or rather, you were taught that angular momentum is I times omega. So I is moment of inertia and omega is your angular velocity. Now, sure, for some nice symmetric bodies which are rotating about their symmetry axis, this is perfectly fine. But in general, L is a vector. So you have Lx, Ly, Lz. And omega is also a vector because you can be rotating about the in 3 possible planes, right? In the xy plane, yz plane, zx plane. And these two are related actually by a 3 cross 3 matrix. And this is called the inertia tensor. In general, the inertia tensor will be some 3 cross 3 matrix. However, you can choose some, if you can choose to work in a basis that is aligned with the symmetry axes of your object. And when you do that, basically you are diagonalizing your inertia tensor. And so you put the 3 eigenvalues, it becomes, everywhere else there is 0. And what you have over here are 3 eigenvalues, I1, I2, I3. And these are your moments of inertia, which you calculate in your 12th standard. So then, if you do this matrix multiplication, you will say, oh, L is equal to I omega, where I depends on which axis you're taking it about. So in general, inertia is a 3 cross 3 matrix. It's only when you choose a certain specific basis along the symmetry axis that you get this. If you are interested in doing this calculation, try it. Take a rod of mass m and length L, and you have already calculated that if you're rotating it about this axis, then the moment of inertia is ml square by 12. If you're rotating it about this axis, then again it is ml square by 12. And if you're rotating it about this axis, then the moment of inertia is 0, assuming it's a thin enough rod. But that's only because you are calculating these with respect to these axes. If you choose some different axis to work with, like this, and this. If these are your XYZ axis, try and calculate with respect to these axes what your summation mi ri square is going to be. And then you'll find not uh, a diagonal, basically you'll find non-diagonal elements as well relating your angular momentum and angular velocity. So that is your complete inertia tensor, which only in a specific basis reduces to the moments of inertia. So that's one classical way of looking at this. Okay, so this is all that I want to say right now. If need be, I might put one more lecture later, but I highly doubt it. These are the basic prerequisites that you need, at least for a first introductory undergraduate course in quantum mechanics. And if you have questions, I'm happy to answer them when we meet in class.